So let's look at an example of using the limit comparison test. And remember, LCT and DCT, as I said before, we often compare with p-series or geometric series. So the thing you're looking for is something that would be easily comparable to one of those two. So it should look like a p-series or like a geometric, but maybe with some other terms in it. And remember, we know from algebra that a rational expression like this, its long-run behavior is dictated by the ratio of those lead terms. So we know that the long-run behavior of any rational expression is going to be comparable to some p-series, assuming the degree on bottom is larger. If the degree on top is larger, we could just do nth term test. That diverges off to infinity. So I know I want to compare with 1 over n, but once you start having multiple terms below those lead terms, it's hard to tell who's bigger or who's smaller. Some of this stuff is making things bigger, some of it's making it smaller. So making a direct comparison becomes problematic. So we really only need to look at the long-run behavior with LCT. We don't care about who's larger or who's smaller. So let's do that. Remember, first of all, the terms of both series need to be positive. Your ANs and your BNs greater than 0. So I want you to state that first. So n plus 2 over n squared minus 4n plus 1 and 1 over n are both greater than 0 for all n. I made sure to start this high enough that there was definitely no problem there. And then we want to look at the limit of their ratio. And remember, just in case we fall into categories 2 or 3, you want the bottom one to be the one that you know the behavior of. So in this case, that p-series should be on the bottom. So let's take that limit. The limit as n goes to infinity of our unknown over our known. Make that a proper fraction. Flip it, multiply that n through. You've got n squared plus 2n over n squared minus 4n plus 1. And you kind of can tell if you chose there correctly, because at this stage, these should be the same degree if we're looking for something that's going to head to a constant. So remember our algebra trick. This is really indeterminate, right? Infinity over infinity. So to make it a determinate form, we just divide top and bottom by that lead term. So we have 1 plus 2 over n over 1 minus 4 over n plus 1 over n squared. Now that's going to 0, 0, 0. This is just 1 over 1, which is 1. Now, that puts us in the first category, right, which is actually the best, because you can always make a conclusion. We end up with a constant greater than 0, so let's say that. I want to see you say you're making your decision there based on the fact that that limit came out to be bigger than 0. And what do we know about this series? The series of 1 over n, it's a divergent p-series. And the reason we know that is because of the degree, remember. It's first degree there. So it's a divergent p-series because p is 1, which is less than or equal to 1. Remember, anything less than or equal to 1 on that degree, divergent. So I want to see all that. That's your argument for why you know this diverges. And so then these two things together tell you that our original series diverges by LCT. So in your argument on LCT, I want you to show me that you understand they need to be positive, so that needs to be stated. I need to see the limit evaluated. Show me what it is about that limit that's making you make your conclusion. the known series. Why do we know that thing converges or diverges? And then your conclusion statement and what you're using there. So LCT, DCT, sometimes you have an option of using either one. Sometimes like this one, you're forced into LCT for sure.